Hello everyone, this is Professor Sergey Sarkisov, and I want to work with us today a very fun geometry problem. You see, this is a triangle here, like given vertices A, B, and C, okay? ABC triangle. And what we're going to do is, we're going to figure out what is that little angle X right there, given that this is an angle measured 10 degrees, this has measured 70, this is 60, and that's 20 degrees there. Typically, we think this is going to be a much easier problem than this one actually is. So let me go ahead and take a copy of this triangle. Let's just work it down here. So let's do this. Here we are. And this is, again, triangle ABC. What do I know about this triangle? Let's look at this. First of all, if this is 10 and this is 70, the sum there is 80, right? This is also, the sum is 80 degrees. This is going to be, because this is equal to this in measure, this is an isosceles triangle, right? So triangle ABC is isosceles, right? And that's interesting, right? So we know AB, for example, side length AB is equal to side length AC, okay? And what I see there also is that this means this angle is what? What must measure that angle? It's going to be 20 degrees, right? Because if that's 80 and that's 80, that's 160 sum, and then the whole sum of angles is 180 degrees, so we need 20 for this angle A. Okay. Measure angle A, or measure angle BAC to be specific, is 20 degrees. Okay. So that's just going to write down all the things we need and can get information-wise from this triangle, we'll write it. Also, look, if this is 80 and this is 60, that's going to be, might as well, we might say 40 degrees, right? 40 degrees. And this one's going to be 30, right? Because that's what? That's, we see that's 70, that's 80, 150 total, and then that's 30 to make it 180. Okay. Well, how does that help us find x? Honestly, it doesn't help us that much. Not yet. What I'm going to do is, I see a really interesting thing I can do. Let's go ahead and let's try to divide this triangle into two pieces. Let's draw an altitude. In other words, let's draw a Chevian that's both an altitude and an angle bisector. It's actually also a median, if you think about it. So look, because it's an isosceles triangle, ABC is, right? So I draw this down, down, and I see, look, this is the right angle and this is the right angle, right? It's divided into two pieces. This is actually 10 degrees here. This is also 10 degrees, right? And because the 20 is divided into 2. What I do see is, look, you see this point of intersection here. Catches my eye. Why? Well, call this point F for a moment. The reason it catches my eye is because if I connect B to F, what happens? What happens when I connect B to F? If you notice and you take a good look at this, what I'm interested in is, look, what is this triangle BFC? Triangle BFC or BCF. Let's look at that. Why? Because look, first of all, let's that point is that was F. Let's call this point G here, right? Or do we have a G there? No, we don't have a G yet, right? So we have a point G here. Let's say let's make it a little more visible. So let's go ahead and write G here. Okay, and so that's point G. Look at this. BG, it might as well equal to GC, right? This is again a median because this is an angle bisector of an isosceles triangle. This is going to be equal. So BG is in length equal to CG. If you can see that. Okay, and then because they're right triangles, see triangle. So that means triangles what? Triangle BG F is congruent to triangle CGF. You can see that, right? And so what happens, the reason I'm doing all this is because then I know that angle, so angle, what is it? Measure of angle FBG is going to equal to measure of angle FCB, right? FCB. See that? So this angle is going to equal to that angle measure, which is 60 degrees. Wow, why am I interested that this is 60 degrees? This is an isosceles triangle, 60, 60. The other angle is also 60. Guess what? So with some thinking, it's obviously 60 degrees, 60 degrees. So it's going to be an equilateral triangle. Triangle BCF is equilateral. Not that it's such a bad or it's not the most challenging thing in this problem, but you know, it's something interesting to look into. So maybe this can help us. Okay, lateral triangle. Okay, now that right away tells us that BC is in length equal to BF and CF. Okay, so that can let that be a start for us also. Now let's go ahead and continue with some other things we can do. Look at this triangle here. How about let's do another triangle here of another another triangle we have with different angles. So look, take this angle 10 degrees, right? That angle A that divided into 2, and then look, let's go AD, okay, and let's go D2F. Let's try that, okay. And actually, let me have extended that. What is it? B. See that BF that we drew some time ago? Let's extend it further to this point here, right? See that point? And let's call this point GH, right? Or do we have H? No, we don't. So H, okay? And so I'm extending that, and by the way, if I draw this DH there, right? DH is going to be parallel, notice, to BC. Not that not that matters that much, I think, at the moment, but let's see. So what happens is the following. I have I'm trying to do this blue triangle, or the triangle in light blue here, A, G, D, F. Okay, let's see why I'm doing that. So what triangle is this, the one I'm doing in blue? It has angles what? Well, this is, by the way, keep in mind, this is what? This line continues, this is 60 degrees, and so right here, this angle F of the triangle here. So by the way, this is going to be 30, right? That's going to be 30. Because it's dividing that 60 into 2 pieces, and this is also 30 vertical angles, right? So this is 30, and you see I have this 10, 30, and you know that's gonna be 140 degrees triangle, right? 10, 30, and 140 left. So I look at triangle AFD. Notice that triangle AFD, okay, that triangle in blue, right, has angles 10 degrees, 30 degrees, and 140. Is there another 10 degrees, 30 degrees, 140 that I can find? Let's see. Is there another 30 degrees I can catch up somewhere? There's 30 here. There's 20 there. Let me think. Let's see. So, not seeing it. Is there a 10-20 triangle maybe I can try? Let's see. Oh, also look. This is an awesome triangle. Yeah, this is 30 degrees. Remember that's given to us, or no, we found that, right? So look, triangle E, and then no, this is also 10, because remember this was 70, so 60 is left, right? And so this was made 60. Remember we purposefully did that so we could get we have an equilateral triangle here, right? And so that's 10 degrees there left, and we have this is 10, 30. Also, so it's actually triangle, what is it, AFD, the blue one, is similar to triangle BEH. See this triangle BEH? They're similar. Why they're similar? 10, 30 degrees also, right? So BEH. This is a very tricky argument. Triangle BEH, because 10 degrees, 30 degrees, and 140 degrees triangles, right? So anyway, we have that. Now let's see. So if they're similar, right? What can we say from that? And by the way, AF. Look at the AF. Let's see. Where's AF? AF is this segment here, right? This line there, and you see. BE, where's BE? BE, AF, FD. Let's see if there's anything we can catch, so maybe we can say they're even congruent, right? Let's even see that if they're maybe congruent triangles. That'd be very interesting, right? So EH and FD. EHFD. Is there a way to show that this length is equal to this length, for example, and measure, or the lengths are equal? And watch this, or maybe AD and BH. Let's see, BH and AD, right? Maybe is this length equal to that one, AD? Let's look at this. We can quickly say that. So BH and AD are equal because BH symmetric to what? To this length DC or CD. So look, so BH also, right, BH is equal to, the length of BH is equal to CD, length CD. So that's interesting, right? Let's lower this just a little bit. And we know CD, whether BH is right here, right? And I'm trying to get AD a little bit, right? So look, CD for sure is equal to AD because that's an isosceles triangle. We said that initially, I think, right? Well, we didn't say that, but this is another argument I want to show you. Watch this. 20 degrees here and 20 degrees there, right? The bigger angle, that whole angle A, that's 20, by the way. So let me erase that for a moment. That's 20 degrees there, that's 20 degrees there. So we know also, we could have said this, initially we could have said also that AD is equal to, the length of AD is equal to CD, right? As, what is it, triangle ADC or ACD. ACD is isosceles. Okay, that's also the case, right? In fact, let me lower that, since that is something that we have just discovered, even though it's one of the lighter arguments. But look at this. So we have BH is equal to CD, which I just said CD is equal to AD. And so we're actually, look, we're matching these up. AD and BH, they're equal. And these triangles are similar. Guess what that means? Triangle AFD is not only similar, it's congruent, right? It's, it's similar and the sides are the same, the corresponding sides, in fact, to triangle BEH. Wow, right? So why is that interesting? Because, for example, the other side pairs are equal. For example, AF and BE. Look, AF is equal to BE, right? Does that help us in any way? Let's see, AF, and AF is this long one right there, and BE is that one right there. There's also, and so this and this is also true, which is what? That FD or DF, right, is equal to HE, right? Or EH. See this? That's really the interesting thing, I think, because look, if we look at this, what's DF and HE? Let me label that actually. DF and HE. Let's have a little purple squiggle, let's say there, and this is there, right? They are equal in length. Okay, What else can I get out of that? Let's see. Look at DF, and you see this is DF. Well, look, this is an equilateral triangle, DHF. It's similar to the triangle below it, right? The one that we knew, BCF. So also notice that DHF and, we'll just say triangle DHF, or yeah, DHF is similar, that's one way to put it, to triangle, the one we had found was equilateral. Which one was it? BCF. Well, let's actually be specific. DHF, or what did I say? DHF is similar to, by the angles, it would be CBF, right? The way that you put in that order, CBF, okay? And so look back up here. What does that mean? That means so is also equilateral, okay? And meaning that DH, which is, now we know already, yeah, so DH is equal to CB, right? Oh, no, sorry. So DH is equal to HF is equal to DF. And we know, you see this this argument here. You see that right there? Again, let me highlight this in different colors. So let's do this a little thicker here. You see that df is equal to he, so put that here. df is equal to he, right? Oops, he. So we have dh, hf, df, and he are all the same. Let's do this again. This is the orange, the orange, the orange. They're all equal, all these lengths. Now, what do you see most important? You see dh, right? You see this one right here. You see that one, EH, right there. They're equal. What does that mean? This triangle, DHE, with the base DE there, this is an isosceles triangle. Wow, right? Okay. So, what was it again? Is triangle DHE. Base, the height being at the top of it being H. So, DEH, let's say that. So, no, so this means that DHF, triangle DHF, let's again see what that is. It's this triangle right here. This triangle here. Right? I'm going to erase that, but DHE, I mean, right, is isosceles. Is isosceles. Okay? With angles, and there's going to be x in there somewhere, right? With angles. What are the angles? So this isosceles, two of the angles are x plus 30 there, right? So let's do this. Let's say, okay, that this is, there's an angle x plus 30 there, and that's an angle x plus 30 there, right? We have to add that there. And then what is this angle? Anyone see what that angle is right there? Well, let's see. That's exactly the same as at 80 degrees, no? 80 degrees. So 80 degrees right there, just like that. Okay, so if it's 80 degrees, what is that angle going to be, that x? We can find it. Because why? Because we can now with 80 degrees and, let me just, not and, but 80 degrees, x plus 30 degrees, x plus 30 degrees, right? Because it's isosceles there. Hence, the sum of the angles, right? 2x plus 60 degrees plus 80 degrees is equal to 180 degrees. And you have x is equal to, right, half of the 40 left, and that's going to be 20 degrees. That is our solution, and I think it's a little more involved than just, adding up to get 180-degree triangles. We had to actually find a little bit of similarity that turned out to be congruence, right, in those interesting triangles there. That look, triangle AFD turned out to be congruent to triangle BEH in the long run, right? So let me just remind us that triangle what was it? AFD and BEH were congruent. What was it again? It was AFD, A. So this triangle here was congruent, interestingly, to this triangle. What was it? Let's see. To that other one. Let's see where it is. I'm trying to make this slower to make it look neater. Okay. That triangle there is congruent to triangle BEH. BEH. And that's not obvious at all, I think. It takes some time to see that. And that's that was one of the biggest arguments we had to go into this final solution here. So those triangles, right? They're kind of not even, barely anything related between them, but really they're congruent triangles. Same triangle, just rotated and moved and repositioned. All right. It was wonderful teaching this, and this actually solving this problem with you. As you can see, I probably definitely wasn't, didn't have the solution right at the top of my head. So this was a really fun exercise. All right. Everyone have a great day, and I'll see you in another problem later on.